Greetings, everybody, from Phoenix. I'm at the Salt River. I just interviewed Nina Fefferman, old friend of mine from the Here We Are podcast. She was on there several times, and I'm coming through Phoenix. I'm recording this actually at the Salt River. I just got some a couple of my inflatable stand-up paddle boards back out of storage, so gonna get some water time in, some outdoors, some activity. And I've been catching up with old friends, seeing what they're up to. Nina is one of them, and she's one of the good people trying to help us all sort through what how us social apes can help work together to better ourselves in a 4 billion year war against infectious disease. And we're all in it. We're all fighting it, whether we realize it or not. And so we're going to be hearing a lot about what science actually does to aid us in that fight. And she is now the head of the analysis and prediction of pandemic expansion, APPEX. You can go to appex.org to find out more and to ask questions yourself, because science is extremely open and just requires people's interest in wanting to engage and learn more. And so there's this is a whole interdisciplinary approach, this program. And so today is starting off kind of a little bit general and philosophical, and learning about kind of how we model reality using math, and then use mathematical models to understand lots of aspects of life, and from biology to social media, and how we put all that together from a bunch of different points of view, and use it to best serve humanity. And this is a really fun thing that I got to sort out, so that you get to hear a few different people working on a similar project to better understand how science works. Because I did my Here We Are podcast for many years before COVID, and then when COVID happened, people suddenly had very strong opinions about science, and I think, especially when they hadn't really engaged with it before. So now, some 5 years later, I thought it would be nice for us to maybe stop feuding, and doesn't that sound nice? Maybe stop getting so political and fired up on social media, and focus on wars that every human can be cooperating with each other against. Wars against, say, infectious disease, and that seems like a cause worth fighting for to me. So I really hope you guys enjoy this episode and the other APPEX episodes to come. Again, that's APPEX.org, and you can ask whatever questions you might have, and they're setting it up so that experts will be able to get back to you and answer questions, and you can better inform yourself and others. Super cool project, and I've just been, so far, it's been a privilege to be back interviewing scientists, especially because I've kind of been doing greatest hits and having some of my faves back on the show first. So I'm going to go get in the water, enjoy Nina Fefferman, one of my absolute favorite people in the entire world, one of my favorite people to talk to, and one of my favorite people to have on the side of humanity. So enjoy today's episode, and that's everything. Okay, Nina, good to see you again.
Good to see you. Thanks for talking with me again.
Yeah, so we first met when we were just kids back then. Simpler times. 2019, you were doing my show Stand Up Science. I'm scrambling around the country getting a couple academics everywhere I'm going to hop on stage with me and talk about their work. And you happen to do a lot of theoretical mathematics around pandemics, and then what do you know?
God damn it! I was hoping to remain a pure theorist for my career, but oh well.
You became applied very quickly. You were one of the first people that I reached out to be like, hey, maybe this person would be able to give me some answers. And we've gotten to keep up a little bit ever since. And now that I have this new show launching, I wanted to have you on, and you have a new project that you're working with. So what is APPEX?
So APPEX is the US NSF Center for the Analysis and Prediction of Pandemic Expansion. So it's building models and analyses, studying data around when outbreaks, when infectious diseases are going to be small and self-limited and only infect a couple of people and then die out, or when instead something about them is going to cause them potentially to expand into a large epidemic or pandemic risk.
Okay, so there's a zillion. I imagine there's several things popping off all of the time, and then there's these kind of base rates in a given area, and then suddenly there's an abnormal number of incidents of either a brand new thing or something that's been around that's increasing in an abnormal way. What's the scariest is it brand new, we've never seen this before, or is it something that you're aware of that?
Well, so it depends what you mean by scariest. So scariest in terms of our complete incapacity to deal with the threat. A lot of those are the brand new ones.
Okay.
Because we don't yet have the tools that would let us even know how to respond to them. So I don't know if you remember, but early on in 2020, when we were just learning about COVID, we didn't know, is it on surfaces? Should people bleach their groceries? Is it in the air? Should people wear masks? Originally, we said, no, don't wear masks, mostly because we wanted to save them in case they were in shortage for medical workers, but also because if it was surface-based, masks don't really help that much and maybe hurt because they get you to futz with your face a lot. And if you're touching surfaces and then putting viruses into your face because you're adjusting your mask, that's terrible.
Right.
If instead, as it turned out to be aerosol or airborne and some droplet transmission, like masks are really good. But early on, we didn't know. And we were like, well, just if you're an untrained person and you're not a medical professional coming into contact with a lot of virus, maybe don't do that so much.
Yeah.
And then we learned more. So the truly unknown ones, we don't really have all of the tools for, and so they can, as we have seen, get a little bit out of control before we know what to do to try and prevent them, even if we do have the tools. But then there are some existing ones that are truly pretty scary, and we would like them not to show up again, even though we know what to expect.
So let me give you, for instance. So there's this. There's this. I'm kind of. You've known me long enough to know that I like doing like weird kind of crazy things that I usually like crowbar into saying that they're art in some way. Mm-hmm. I have this idea of there's this place We Spa in Los Angeles. It's like a very cheap like 24-hour spa, and the life hack is that instead of like getting a hotel, if you have a layover, you can like sleep there on mats and like
nice.
and every time I go there, I'm like, I think it would be fun to spend a month just living here to see what would happen. And my first thought upon having that was, I wonder if I would get some rare bacterial infection that like has never existed before in any way. Like I'd have to go to the hospital. At first I wouldn't tell the doctor I would see if they could guess first.
Okay. So and
then I'd be like, I should probably let you know that I've just spent the last 30 days in a weird spa that doesn't have the most hygienically friendly things going on. So I'm creating a situation, a hypothetical. I'm patient zero.
Yeah.
I'm just like, there's been some abnormal viral load that I've put myself in. It's expressed itself in some way. And now it's, I don't know, some fungal infection or something like that. It just starts spreading around. No one's ever seen anything like it before. How do you manage something like what are the first questions that come to mind?
Sure. So first off, just to disclaim for the poor WeSpa, what the scenario you suggest is unlikely to breed a novel infection. It's possible, but it's unlikely.
Okay.
Because that scenario would have folks exposed to it as they came through. And the fact that you're there constantly would mean that, yes, you're exposed to all the people there and whatever's growing there. But in order for it to be truly novel in that context, it would either have to mutate in the walls of the WeSpa and then get into you through the duration of exposure, as opposed to the person who just came through because it's Tuesday and happened to be there the day it mutated.
Okay, all right.
And there are diseases that do that, where constant re-exposure increases your probability of catching an actual manifestation of disease instead of just like picking it up and having your immune system be like, nah, we're good. But they're rarer. Most of the time, if there's enough to infect you, there's enough to infect someone passing through.
But there are viral loads and containment things that happen especially with biodiversity loss and more. I know I'm taking some leaps here.
I just want to reassure the users of the users of the WeSpa they're unlikely to be patient zero as a result.
WeSpa. This is the weirdest plug for a business ever. I hope they give me a free pass and not a lawsuit.
Absolutely.
For this mention, but
yes, okay. Let's presume that it came about. Let's presume that you are patient zero.
I'm patient zero for something.
What happens? So the first couple of things that are crucial, even to us identifying that something has happened. What is the clinical manifestation of the disease in you? Does it look a lot like seasonal allergies? Does it look like food poisoning? Does it look like does it look like flu? Almost everything starts out looking like flu somehow, right? And so we even have a designation called influenza-like illness, where we don't even bother diagnosing it. We're like, it's something like flu. It causes flu-like symptoms. And so, in fact, many of the labs that do clinical testing for influenza in the United States switch over to not doing much testing during the summer because we expect influenza to be seasonal as a winter disease.
Right.
And so the testing capacity goes down, which means that many things that actually are flu are diagnosed as influenza-like illness in the summer because we don't bother sending them to a lab because there are just fewer labs. We're like, probably flu-ish, do these things. So the first thing that we would wait is to see what's different about this thing. So if you're patient zero and you start spreading it, we'd have to actually wait to see wait, there's more people than we would expect having some unusual symptoms right now. And they're presenting kind of the same way.
Okay.
And then we might start asking questions like, did they do anything in common? Is this an environmental exposure? Did they all go to WeSpa? Did they all eat the tuna? Or is it, are they all people over a certain age? Are they all people with a certain history of heart disease? Are they all? So how would we find both what's unusual and then what's common among what's unusual? But even noticing such that we would start asking those questions isn't easy, right? You might go to your doctor, you might not. It depends on the severity of the symptoms. You might go to your doctor before you pass it to 3 other people. You might not get to your doctor before you pass it to 3 other people. Those 3 other people might in fact be 20 other people, depending on what's true about the disease. How quickly does it go from you've caught it to you can transmit it to other people who then catch it? That generation time is really important for what looks anomalous or not. So a few people have influenza-like symptoms in the summer, fine. 70 people have influenza-like symptoms on Tuesday at this clinic, not fine. So it's what's different, what's the same, and then what do we start seeing? What comes across whomever is keeping track? Sometimes the folks keeping track are the doctor's office or the clinic or the hospital. Sometimes it's the diagnostic lab. And so that has to wait for different doctors to all decide to order the same clinical tests that all then use the same diagnostic lab. And the diagnostic lab goes, we're getting a lot of these requests. We don't normally get this many requests. Oh no, something's weird. Sometimes we have to wait for it to get into a wild animal or a domestic animal, where we go, yeah, that strange thing happened to Shane, but I don't know, maybe just strange things happen to Shane. But but now there are birds falling out of the sky. That's how we figured out West Nile virus for a while, right? As like before we figured it out in humans, we were like,
really?
Oh, crows are literally dropping out of the sky. That's not good. What's that? And so West Nile virus, even though we are worried about it in people, was originally, I believe, isolated because I think there were both ornithologists and zookeepers of birds in, I think, New York, that went, we're seeing really strange patterns in bird deaths. This isn't good. We should figure out what's going on with this. And then we figured out, like, oh, this is also a problem for humans. We don't actually know if there were humans who were infected with that first. We wouldn't really have noticed. We wouldn't have known what to look for. We might not have diagnosed it appropriately or correctly. There probably weren't very many. Relative to birds, it's much less frequent in humans, even when it's a really bad West Nile year in the US. So what we look for, what we notice, what's different, it's really dependent on the scenario.
And what about, so early on, and so it must be so difficult to, even in terms of what a doctor gives someone. So someone comes in who is expressing some flu-like symptoms, and then they're like, well, clearly water's on my mind. They're a sailor or something like that. So say they're treated with vitamin C or something just for kicks, and it makes them better because they had scurvy in addition to whatever other
For the record, we try really hard not to let sailors get scurvy these days, but yes.
Okay, just a for instance.
Yes.
So you have something else that is hindering your health and keeping your immune system
of some form
very occupied, and then you do something that frees up some of the energy potentially for your immune system, and your immune system is more equipped to take on whatever this novel threat is. And so then it looks like, okay, but we just give everyone vitamin C and that ought to fix it.
Goodness.
You know what I'm saying? Like for instance, maybe a more broad example is if you're working with, say, a malnourished population and you nourish them.
So actually, that turns out to be tricky.
Really?
So yeah, one of the first, this is actually rather creepy research, but it's really important. So one of the first actual empirical research studies that this is not my research, I was helping out, but this was not my research, but it's really cool, important research, and I was proud to help out, but you'll hear how creepy it is in a second. It turns out that if you take malnourished children in the developing world, a leading cause of death is respiratory infections. Not even attributable to a particular pathogen, just all-cause respiratory infections. And if you give them vitamin A and zinc as a micronutrient supplement, their survival rate from respiratory infections increases. It's really good. Unfortunately, if you take a well-nourished child and give them vitamin A and zinc, their probability of surviving respiratory infection decreases.
This is exactly what this is what I was trying to say.
And then there's a really creepy research question, which is, what is the boundary between a well-nourished and a malnourished child? How do you decide whether to give the child in front of you? If you're a clinician, and this is research in Ecuador, if you're a clinician in rural Ecuador outside Quito, like you travel into the jungle, how do you decide whether the kid in front of you is going to be helped by provision of vitamin A or zinc, or harmed by provision of vitamin A and zinc? And it's actually a very tricky question. And so there was active research, this is 20 years ago now, but there was active research at the time of what if these are the clinical signifiers of well enough nourished that we don't do it? Let's try a cohort study where we define it that way and see how many kids survive. And then we'll try refining where we draw the line and see how many kids survive. And luckily, I think all of the people involved in that study were incredibly ethical, careful people who really, like, their goal was to help kids. But it's a creepy study to be involved with, where you're like, well, hope we didn't kill too many.
Yeah, well, because it's using the best information that you have at the time.
Yeah, but you are absolutely studying to improve the information.
Right.
Because at that point, we knew already that if we got it wrong, we were doing harm. So withholding the treatment from malnourished children was doing harm, but giving the treatment to well-nourished children was doing harm.
Right.
And so it really was a harm minimization, help maximization, constrained problem. And it was a thing.
Right.
And so that's never easy, because especially with a new disease, like that was at least for a well-established population where we kind of knew what infections they were exposed to. And the question was just, how do we help? If it's a new infection emerging, or it's in a new population and we don't even know what the measurements are of success, what is a baseline, right? There are these famous stories throughout medicine, not even having to do with necessarily directly treatment of infectious diseases as we normally think of it, but like amputations in this, like the reason that we discovered that it is not a good medical practice to seal off the wound from an amputation is that literally Civil War amputation surgeons ran out of oil, because it was best field medical practice to saw off a limb as quickly as possible and then dunk the stump in boiling oil to cauterize it. And a poor field surgeon ran out of oil and was like, oh my God, we're going to have to dunk the stump in boiling water.
Without
the
oil.
Patient is going to die, but I guess we're going to do it anyway. And then all of his patients did much better. And they were like, shit, maybe it shouldn't be boiling oil. But until you discover that.
Right.
And that is about pathogens a little bit, because its cautery is to prevent infection and death from sepsis from the wound. But it's not really treating infection; it's preventing infection by cautery. But
so then, for the average kind of listener, I know that I love attempting to communicate science. I'm not a scientist. I don't know everything involved in a lab, and I know that it's a whole nother layer of complication trying to explain science to someone who isn't interested in it. And there's one of my favorite subjects is just cognitive biases and the many ways in which I love, I'm an irrationalist. Like, I love the ways in which the mind comes up with conclusions that don't match reality in all these predictable ways. And I'm wondering if you could maybe help break down how science approaches taking anecdotes and it takes that the difference between anecdotal evidence and data analysis and running a controlled study.
With pleasure. So I think that's actually the definition of science. So the definition of science is the process by which you generate knowledge and generate belief.
Yeah.
And in a very real sense, science is a way of knowing things. It's not the only way of knowing things, but it is a process after which scientists, especially, but also people who listen to scientists, go, okay, now I know this by this process, by the process of science. And anecdote is very much part of it, but it's the very first part. It's someone making an observation or thinking about things they have observed or been told or know in another way and going, I wonder if the process of science, which is a process of interrogation, of going, let me see, can I make a prediction about what should be true if that anecdote told me the thing I think it tells me, if that thing I now believe that I know, or I know by another way, if that belief is true? What else should be true? Or what should I be able to change about the system in order to then see how it's working to make sure it's consistent? And so that's really what science is. It's that interrogation in a way that says, let me start with a supposed belief and then interrogate it in a structured and formal way. And it's not just formal that I interrogate it, it's formalized in a way that if I describe that interrogation, someone else performing the same interrogation of the belief would get the same answer that I do.
Right.
And that's where repeatability and independence comes in. And scientists seeming to sort of waste time replicating studies. And the answer is it's not a waste of time because we all make these assumptions that we don't notice of like, I did this experiment and it was 60 degrees in my lab and someone else did it and it was 74 degrees in their lab. And I didn't write down that it, like now we know to write down the temperature in the lab, but we didn't when we started. And it took people replicating those experiments and going, I didn't get your answer. Why didn't I get your answer? What was it about what we now think we believe that isn't true?
Right.
By knowing it by science. Oh, maybe temperature is important. And some of these aren't about necessarily just lab studies. Some of them are fantastically about, one of my favorite temperature things is actually about animal cognition, where in the 30s through the 50s or so, scientists got really excited about categorizing animals by how smart they were. I'm not sure why, but we got really excited about this. And so there were these series of tests where we decided, we writ large, humans, including scientists, decided that these tests were the ways to measure animal intelligence. We're going to put a bunch of different species through these tests and see the intelligence of species. And some of the, and we did this to a bunch of things, and we were like, these are very smart animals, these are not very smart animals. Okay, we know this now. And maybe like 10 years ago, 15 years ago, someone went, guys, when they did these experiments in the air-conditioned lab environment in the winter, did anyone warm up the tortoises? Tortoises are ectotherms. Their blood flows to their brain real slow when they're cold. How cold were the tortoises? And so someone just like 15 years ago literally warmed up some tortoises and put them through exactly the same experiment. And they were like, oh my God, tortoises are freaking geniuses relative to what we thought. Which I think is so funny on so many reasons, for so many reasons, because also I don't think there are a set of particular intelligence tests that really just work across the animal kingdom, but also what it really proved was that humans were being stupid as opposed to tortoises were being stupid.
And it's also very human to hold on to beliefs that you're excited about and everything else. But what I love about not every single scientist, but certainly what science is really excels at, and the people that I seem to meet that are doing it excel at is discarding things over time when it doesn't work out. And I there was a good quote recently in a conversation. Italian and I at NYU Medical School we were talking, and he was like, well, if there was something better than science, scientists would use it.
Yeah.
And I think that's...
Well, so there was something demonstrably better. So, right, it's a way of knowing things. And I think that's also why scientists are so comfortable. We're human, we can get attached to our pet theories.
Of course.
But in our training and when you calm down and take a deep breath, I think all scientists and probably all engineers, also like even broader than just like strictly the scientist, I think anyone in STEM, the process is the thing that excites us. And the reason that process is exciting is that when it's wrong, it knows how to move on and fix it and correct. And it's not because the new thing is right with a capital R. It's because it's the best knowledge we've generated so far.
Right.
And when we learn that that's wrong, it's exciting to reject that and figure out something better.
Right.
And so when we say science says blah, 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 we're not saying we know this because there is an authority of science that says it. We're saying we know this because we've interrogated it. And all of the interrogation we've thrown at it so far has said, this is it. And some things are so well studied that we go, okay, it's possible it could be wrong, but then everything we know about everything is wrong.
Yeah.
Like we could all just be brains in jars, right? Immanuel Kant, philosophy experiment. Maybe we are a hallucinating brain in a jar and there is no external reality and we're just making shit up to ourselves.
Right.
That's still technically possible.
Yeah.
I'm not going to bank on it, but it's technically possible. But when we say like science has established this thing, what we mean is it is so consistent and we've interrogated it in so many different ways from so many different perspectives. And we've made so many different predictions and tweaks and experiments and we've done so much theory. Not just we've manipulated the real world, but then we've been able to write down a why. And then we've been able to say, well, if that why is true, what else should be true about that why? And then we've gone like, yep, that other thing is also true if this why is correct. So, but we still, because we're so trained in science, we very rarely then go like, okay, we know it, it's just true. We go, science thinks so, or we haven't disproven it.
I think that's frustrating for people that want simple answers that they can have a bunch of confidence about, and well, because it's also like just moving forward in life, and just the intimidating amount of
unknown. But I think it's both reassuring. I'm going to say I think it's both reassuring and terrifying all at the same time.
Yeah.
There's the reassuring part, which is sometimes I think people who aren't scientists have never been told that when scientists say, well, it's not disproven, but we're real sure, they hear uncertainty.
Yeah.
Whereas scientists are meaning to communicate certainty right then. It's just certainty to the best of human knowledge.
Yeah.
And that's a lot of knowledge. Humans, we're not brilliant as we want to be, but we're also really not stupid. And we've been thinking, like very smart humans have been thinking about some very challenging things for a long time. And if it's all consistent across the board, we can be pretty confident that those things really are operationally true.
Right.
And that's not true with a capital T like a philosopher's true.
Yeah.
But it's true with a lowercase t. You can live your life based on knowing this.
Well, I think that there is some, there's a, because I could sit and rattle off, 30 different things that I think factor into people's difficulties around science, or the difficulties around communicating them. But I think that there's such what I really love about math, for instance, and science generally, is that I do think that there is an opportunity to potentially get on the same page with one another, and we can show each other our work. Where mathematics is the foundation for physics, which helps we use to build chemistry, then biology, and neuroanatomy is psychology, and sociology, and then we have philosophers working on that big T. But we are all kind of philosophers. We are, to a lesser extent, cultural commentators, and then to a lesser extent, we're all doing psychology and economics in our own way, and then to a much lesser extent, like maybe I'm mixing some creamer in with some coffee or something, but we're chemists to a much, much smaller extent, and anyone will sit and have a philosophical conversation, but it's very hard to agree on a philosophical conversation. Whereas like something like algebra, x plus y equals z, or something like that, is something that even if we're coming up with different answers, we can sit down and figure out together why z is what it is. And this is, I feel like I can speak to someone that's in Japan about this. I feel like if an alien comes down tomorrow, I can talk to their mathematician, and once they figure out what I mean with this equal sign and this plus sign, we're going to be rocking and rolling much sooner than we are understanding each other's verbal
this
language.
is also why I think there is a big distinction between mathematics and science. So science is, as I said, a way of knowing things that interrogates based on conjecture and then experiment. Math is internally logically consistent. Math is a way of retelling yourself something you already know in a way that you discover is a new way of expression. But that's why two people who don't know each other and don't have the same method of expression can sit down and go, do we agree on what objects are? Okay, then can we agree on how to count objects? Okay, if we can agree on how to count objects, can we agree on this operation called addition, which means taking this many objects and this many objects? How many objects would we then have if we counted them together?
Right.
And then can we agree that that's really kind of inefficient? Sometimes we want to add objects a certain number of times so we can multiply them.
Right,
That's
right.
multiplication. Okay, what happens now if you don't care what the operation is? It doesn't have to be counting them together. It could be any operation that you make on numbers of objects.
Yeah.
Okay, that's an operator. That could be addition, subtraction, multiplication, division. All right, so now how do we write that as a function? Okay, it's an arbitrary function with some operational things on groups of objects.
Yeah.
Maybe those groups of objects themselves have some rules about what kinds of operations work on those groups. And then in math, those stop being sets and start being what is actually called a group in English.
Right.
But those are, every time that I say that next thing, there's a logical rule that lets me impose it.
Right.
And it is then true with a capital T. There's no suspicion.
Right. Like
yeah.
we're sitting, I see 4 buildings around. Like if I'm giving the information that there's the same exact number of rooms in every single building, and I know that there's 50 rooms in this building and there's 4 buildings, I know that there's 200 rooms, and we could go and count each of them. We could have 100 different people count each of them individually. And
so the
if we
counting
came up
might
with
be
different...
science. Yeah, the counting would be science because there can be observational error.
Right.
But the calculation, if you tell me that those things are true, the math that takes over, that calculation of 200 rooms, that's correct.
I see. Okay, so because like if we get other answers other than 200, all that we're finding out is who's bad at counting, essentially.
Pretty much.
And so that's. And then so you can expand on this and we can go like, oh, actually there's 8 buildings, same rules apply, and you can do this with anything, anywhere in the world.
And that's how you build up the more theoretical branches of math. So the applied branches of math are still tied to some observations. The theoretical branches of math are only tied to those mathematical objects or those mathematical operators. And that's where you get really beautiful theoretical mathematics that, by the way, can still apply to the real world, but it's not coming from those observations and measurements. It's now coming only internally, consistently from the logic of mathematics. Can you tell I love math? I love math so much.
So do I. It's been a long time, but I've been itching to like, I need to restart from the beginning. It's been so long. For
the record, we're doing some very cool math at APPEX, not just applied stuff. We're doing some very cool actual theoretical math at APPEX.
I'm that's fascinating. I wish I would have kept going with it. It was
Never
the only
too late.
subject. I know.
Come to the dark side.
Yeah. It was the only subject I liked when I was a kid. Well, can you reframe this one more time, because I was excited by what you're saying and also trying to follow all of it. The difference between mathematics and science. This is really interesting, because so I'm thinking about mathematics as conceptualization of objective reality. Right?
So it includes that, but then it goes beyond it. It's the conceptualization of the imaginary also, of things that aren't real.
Oh, so this is like theoretical mathematics, but also...
Yeah, but it comes from... So all of mathematics, whether it's applied or theoretical, comes from the idea that the important things are the rules. And then all you're really doing in all of mathematics is discovering, and it is a process of human discovery, but it's the intellectual discovery of discovering the new things that were true already whenever you applied those rules, that you didn't think about that consequence. And the things that mean more and more intricate, beautiful, complicated, amazing things that are just true because you happen to say, like, yes, in geometry, the shortest distance between 2 points is a straight line. That's an assumption that you can make, and then you have that rule. And then you can explore what is true in geometry when you have that rule. You don't need to have that rule. There are geometries where that rule isn't true. Think about a geometry on a sphere, on top, like on a ball.
Right.
The shortest distance between 2 points is an arc.
Right.
And then, because if you have to stay on the surface of the sphere, a straight line this is actually also how planes fly, right? If you look at your flight path around the globe, if you look at the Mercator projection of your map, it's very rare for it to look like a straight line. And the answer is because it's the shortest distance. It's frequent. Like if you fly from the US to Europe, you're flying in, from our perception, up towards the North Pole, towards the Arctic, and then back down into Europe. And the answer is it's a shorter flight than if you just went across the Atlantic Ocean.
Well, so now things get really complicated when we factor in human factors, because this is you're taking something, all this, the best and the brightest mathematicians, and then figuring out what that math says about how to think about public health and potentially individual decisions or some guidance or advice or whatever else. Science doesn't do a lot of shoulds in my experience, but
prediction, knowing what we think will happen.
So then you make these so you have this logic where you go, okay, shortest distance straight line. And who was it? Eisenhower that made the first interstates is like, well, if there's bombs, we need to make this. We need a straight line. We need to beeline it the heck out of major cities, or be able to get to big cities, and then realize, oh, when you do that, when people sit and hypnotize themselves on a straight line for hours at a time, they fall asleep and drive off the road. So that's actually like a beeline to death for a lot of people. And it turns out we need to put some curves in this road to factor in the human experience, which is something that we're now with we're dealing with on a very practical level of like, we're here in Phoenix where there's, I don't know if you've taken a Waymo yet.
Not yet.
They're great.
Yeah.
Fingers crossed, it all goes well. But I just took my first one. It was a lot of fun. And it's really easy to see how much sense all self-driving cars makes. And it's really easy to see how hard it is to introduce or a couple self-driving cars. But the intermediary space where you're like, okay, this is mostly self-driving, but we need you to pay attention to only 0.001% of the time, but it's the most crucial time, and it's going to keep you from dying. But pay attention the whole time, but like without having to do anything.
Yeah, we're gonna get it wrong a couple times before we get it right. I think
that's so. How do you take something as clear as mathematics and then apply it to the human experience?
No, so this is, I think, the most fun, and this is what I love doing the most. And the answer is that it's collaboration. It's no one person doing this. It's teams of scientists from different perspectives. So it's behavioral psychologists, and it's doctors, and it's cognitive psychologists, and it's mathematicians who do the storytelling around, okay, tell me what the experimental psychological theory is around how humans think about this. And a physiologist going, tell me what someone's blood pressure does when they just sit stationarily and stare at a point in the distance for 4 hours. Right. Tell me what a neuroscientist, tell me what someone's neural waves look like. Are we going to give people epileptic seizures if we flash lights at them to keep them awake?
Right.
Oh, that's bad, right? So it's all of these different components of different sciences that study the story of reality.
Yeah.
And then you sit down with a mathematician, a mathematical modeler, and start telling that story. And the mathematical modeler asks some really weird questions that the empiricists don't think of, don't approach that way, don't think of as assumptions, don't think of as part of the story.
Yeah.
Kind of like the cognitive scientist being like, what temperature was the tortoise?
Yeah,
right?
Yeah.
Mathematicians ask questions like, what temperature was the tortoise? Because we're hearing from some physicists and physical chemists that some things they think about are temperature dependent, even if the behavioral psychologist isn't thinking, or maybe the behavioral psychologist is thinking that and going like, you know what, people are nervous when they're cold. Or, people don't fall asleep as easily when they're cold. Maybe the room should be cold, right? So these kinds of things where by being a little bit of an outsider. Also, the mathematician is good at putting the story together. And then exactly as you said a few minutes ago, mathematics is an excellent language for translation in clarity. And so it's really hard work to make it clear and to make it rigorous. But once you write down, here's the mathematical representation of what we want to say, everyone can check it. All of those different disciplines can go, all right, I need to ask a zillion questions because I don't really understand the representation. Maybe I don't understand. There's a squiggly thing. Like, is that an integral or is that a approximate thing? Like, what does that symbol mean? But when you dig into it, then everybody can ask their own questions and really see the common language that math enables. And then it also makes it quantitative. It makes it a prediction that we can then say, and then you should be able to go measure that thing. And if we're right, the measurement should go up on Tuesday instead of down. And if we're consistently right, when we say like, and then it should go up again Wednesday, but down Thursday, and up Friday, but down Saturday and Sunday. And if we're consistently correct about that, that's when the math helps produce the science of the observation of, did the math, the purely logical, purely constructed, not observationally dependent, no experiments happening, but did the math predict the thing that we think captures the theory and the science, and then can we do the experimental science to see if we assembled the right story? And if it didn't, we go back and say, what did we miss? And if it did, we go, all right, maybe we're getting somewhere. What's the next piece we should test? What's the next thing we should throw in and see if that also affects what's going on? Do we really understand it, or do we just understand part of it as long as we don't change the temperature, or part of it as long as we don't change the species, or change the pathogen, or change the time of day, or all of these things that we didn't even think of that are assumptions in the observations we made that made us tell that story in the first place. And then we go, with math, we can do some science experiments and do the hypothetical. What if we think it does it this way? What would the answer be then? Okay, let's try and test it. Or okay, let's do the math and then wait for it to someday happen and see if we were right. Some things we can't make an experiment about, but we can have the math to predict in case it happens. And when it happens, we go, ha, look, it did it. Or, oh, we did not get that correct. We should go back and try that again and then see if it ever happens again to test it the next time. But we know we were wrong. We know we missed something.
Right. And what's the difference between quantitative and qualitative?
Sure. So qualitative. So there are big methodological differences. The ways people are trained to do qualitative versus quantitative science are very different. But at its core, the only thing that's different is the nature of the storytelling. So quantitative research or storytelling is about numbers, is about the magnitudes and the operational, those arithmetic operational relationships in the story. If I do this, the numbers will go up by this much. If I do this, if I turn this dial by 3 degrees, I will get a 20% change in my answer. Those are quantitative interrogations because there's literally a quantity. It's literally a measured amount.
Right.
Those can be predicted amounts. They don't have to be observed measurements, but there's a measured amount. Qualitative are relational. Qualitative can include some quantitative things, but it's more about the relational things. Going up or down is qualitative if you don't say how much it goes up or down.
Right.
I will be happier. How do you measure happy? Subjectively self-reported. You could assign a number to it, and some people do. Some people are like, here's a happiness scale. Point to like the smiley face on the scale that closest represents your feeling right now. But also, you don't know if on a different day, feeling exactly the same way that you feel right now, you would point to the same smiley face.
Right.
We make experiments about that, and we see what people do, and we have some expectations. But we know that humans aren't really consistent about it. We know we shouldn't quantify it. We should leave it qualitative. We should leave it as, yeah, this is basically good. It's not 0.73 good. It's basically good.
Right. Well, so how much science can, like, the general public, I guess, reasonably be expected to know and understand, and what are some I mean, a thing I've been thinking about lately is just like, there it's as there's been I've been doing science communication for 14, 15 years, something like that. It's gotten markedly harder since COVID, and I don't think anyone's made a secret of that. And there needs to be there's some clear lack of trust issues and we can set aside whatever reasons that might be, but for people to live their lives, mm-hmm. they have to be able to know if they get in an elevator that an expert had, built that elevator and checked that elevator. They know they have to put some amount of trust in their GPS to be able to drive there, or that their Waymo that they get in isn't going to go careening into a ravine. And that is all built on science. Science is building the many things that are. This is humans. When humans first thought about the world not being flat, it wasn't going to change anyone's day-to-day life if they woke up tomorrow knowing the world was round or not. Now, if everyone has amnesia tomorrow and no one knows that the world is, despite the intuitive feeling, like it looks very flat to me right now, that it's not round. I mean, there's who's managing satellites, who's doing
we have problems.
So our modern world is increasingly dependent on some level of dissemination and public understanding of some basic principles, or at least some amount of trust and knowing what to trust. It's
right. So I'm going to twist your question a little bit, and I hope you'll let me.
Please do.
So I think instead of how much science do we expect someone who's not a scientist to know to operate in public or to trust science, I don't think it's the right question. I think the actual answer is, how do you know when you trust something?
Right.
And I think that's not about how much science do you have to know. It's about how much do you understand the process of science. And I do think that that's where we failed as communicators in elementary school, in middle school, in high school. What does it mean to know something in science is about that process, not about the fact. We teach elementary school students a lot of facts, and we say we know this because science. And as an elementary school student, it's very reasonable to hear science tells me in the same way that my parents tell me. And therefore, it's just proof by authority, which is a different thing from what scientists mean when we say we know this because science. And that means also, if instead we taught the process of science, people would know science is fallible, but when we're wrong, we go correct it. And then we tell people we were wrong. And it's not the same. It's also not trusting a scientist.
Right.
A scientist can be wrong a lot.
Right.
Science involves a lot of peer review, and we're generally evil to each other about peer review. We're not that kind. Even very kind people are not kind in the context of science. We don't suffer each other's mistakes because the thing we're all doing together is science. And so when we think someone else is making a mistake, we stop them and we go, "Are you sure? Tell me why you think that.
Right.
Convince me." And so it's also the case that when we think about science, the consensus of the majority of scientists is not an easy thing to assemble. This isn't groupthink. This is everyone has been fighting a little bit, and everyone has been independently convinced for their own reasons to be like, all right, I'm there. I get it. If I think tomorrow of a reason why it shouldn't be true, I'm going to tell everybody. But everyone's convinced me so far of this.
Right.
And so that's also true. We never get 100% consensus of anything.
Right.
There are still flat earthers, God help us. I actually can use math to prove they're wrong. It doesn't matter. There will still be some flat earthers, and some of them will have PhDs in science because that's just how life works. But when we as scientists communicate to the public, there are two different kinds of communication, right? There's the peer-reviewed literature where we're not talking to the public. We don't mean to. We're actually terrified sometimes if the public reads it because we're talking to each other as scientists. And we're using jargon. And that jargon communicates specific things to other people who have been trained in the jargon, because the whole reason for jargon isn't to keep people out. It's because we're lazy and it's a shortcut for other people who were trained in it, who know the jargon. And instead of using 700 extra words, we can just go blub. We know the 700 extra words behind blub, right? And if we're trained together, everyone goes, yeah, blub, we got it. But if you're not trained in it, especially because science loves borrowing existing words, so I just used blub as an example, but I could have instead said red. And if I'd been like, when I say this thing is red, like we have colors of noise, right? There's white noise, there's brown noise, there is pink noise. If I'm talking about noise and I say it's pink, you and I might know about that if we know about how to think about sound and noise and entropy and physics. A layperson might be, what on earth do you mean the color pink is involved in this? Right? And the answer is it's jargon, but it's useful jargon because we have to communicate efficiently. And so when we write scientific papers for each other, we argue back and forth all the time and we criticize each other and we use jargon to do that. And we don't mean the same level of communication that we would be using to try and communicate to someone who isn't not just even a scientist, but a scientist in our own discipline that knows the same jargon. And so some of what we are trying to do, I think, misses it because we didn't teach kids in elementary school and middle school and high school not just the facts of what science thinks is established, because most of those are. Most of those are established facts. But really the important thing is, what is the ongoing process of science that will come back to you, not when we're arguing with each other, but when we feel like we've settled it and gone, you know what's ready for prime time? A self-driving car. We have established enough facts about the engine. And honestly, the first couple weren't ready for prime time. We put them out on the road and then experimented with them. We're like, oh God, they weren't trained on enough different people. They're ignoring entire categories of people because we didn't show them enough pictures of different people. Or they don't know what to do if somebody disobeys traffic laws. We didn't tell them that sometimes people do stupid shit in cars. Right? So and then we had to go back and revise. But when we rolled those out, like some industry rolled those out, but like science didn't roll those out and say, guys, it's time for self-driving cars. We were like, we're really excited. In the next 5 to 10 years, we think it's time for self-driving cars. And then somebody being excited usually writes a journalistic article that says, science says self-driving cars will be a reality in 5 years. And that's not really what we said. We said, like, we think we're about 5 years out from this being a good plan. But that's because we have extra stuff to do and we haven't done it yet. And so I think if we, instead of asking people to know more science, if we just ask people to know more about what it means when we say, this comes from science, this is the process by which science works, I think we'd do a lot better at trust. I think we'd give people a lot better operational heuristics, right? Because we're thinking fast and slow, right?
Well, people say science, though. Like, people will say, like, hey, this is scientifically proven or whatever. They're like, well, they use the word science. I don't know. It's still...
We can't restrict what people say, right? I love this. There's actually a Facebook ad that I'm embarrassed to say sometimes I am still on Facebook. A Facebook ad popped up to me the other day and tried to sell me an NSF certified water filter. And because I happen to be a scientist, I was like, the NSF doesn't certify water filters. That's meaningless. I'm glad you can write it, but like, and you should be able to write it, but it's snake oil. It's bullshit. Don't buy your water filter because someone says it's NSF certified. So people can say all sorts of things. And I don't know that we can fix that with anything having to do with science. That has to be more about what public trust has always been about, community, right? And how do we have community standards for who gets to say things that are unquestioned versus who gets to contest what people say? And how do we as a public forum converge on, are you the right person to say that? Because maybe if you're a community leader and we trust you, but you're not a scientist, maybe you don't get to speak for science. Maybe you get to speak for community standards and and maybe you get to guide how we go find the scientists and talk to them. But maybe we're not you're not the person who should tell us about the science. Maybe the scientists should do that. And maybe the scientists aren't the people who should tell you about community standards.
Yeah.
And there are some scientists, for the record, who study community standards, and they should.
Yeah.
But that's a narrower thing from, like, a mathematician should never stand up and be like, I know what everyone should do. They should stand up and be like, here is what my math says will happen if everyone does this.
Right.
And then it's, as it has always been, about community decisions about what to adopt from those practices. Right? And that's why also we have sort of cultural horror stories about cultures we don't understand how they decided to do things, right? We have stories about historical otherness cultures of like religious sacrifice to sun gods, right? Whether or not that's actually true, that it happened, it doesn't matter. We can tell ourselves apocryphal stories about like that crazy culture that sacrificed people every day so the sun would come up. We shouldn't do that. But there was a cultural norm in assuming that this existed. There's a cultural norm that says, yeah, we should do that. Do you want to risk the sun not coming up? We all agree.
Right. Well, I mean, this goes to understanding concept. I do think that you're absolutely right that I think it was like Jeopardy and trivia got kind of known as like, that's how we test intelligence. Like, how many things can a person memorize? And then I think that outside of math, I guess like maybe some language skills, concepts were really, because even history class was like, know the year that this happened, not the concept that, and that would, I mean, I think if people can kind of wrap their head around some of the broader concepts that answer more of the like case study type things.
Yeah, and I think history is a great example because I think the way we teach history is just as misleading as the way we teach science.
Yeah.
There are so many amazing historians right now who are active research historians.
Right.
And they are not repositories of encyclopedic names and dates.
Right.
That's not what they're doing. They're not going out and discovering what year this thing happened. They're understanding the causality of the sequence of events and the understanding of events in history that led to the outcomes that occurred and were reported and recorded, and those differences in how things are reported and recorded. And I'm not a historian, so I don't even mean to represent history, but it's so far removed from history class in high school. Even advanced history, like AP history, starts giving you hints about what real historians do. But I don't think if you ask the member of the public who isn't a historian, what does a historian do? I think they'd be able to tell you maybe they teach classes in history, and they probably know things that happened in history, but they wouldn't be able to tell you what is a working historian. What does a working historian do?
Right.
And I think that's that same separation. What does a working scientist do? And that's the same separation of, yes, there are facts we say science has produced in the same way that there are, Napoleon was defeated at Waterloo.
Right.
That's not what a historian does.
Yeah, I was just kind of thinking of. We'll wrap up in a moment.
Sorry, no, I was just checking.
I was thinking about. I've been thinking a lot about how showing the ways in which our beliefs sometimes overlap reality and become knowledge, and there's this intuition that over time and experience that those beliefs just overlap more and more of objective reality, and sometimes you can get further and further away. But I was kind of thinking about what happens once we know things, and I decided to just pick cosmology. I picked Mars, for instance, and Mars, as soon as there was written language, there's myths about it. I presumed that because humans had used stars for a long time to navigate, that there would be grand stories around them. And so I was like, I'll pick Mars since you can see it with the naked eye. And there was Hindu mythology and astronomy. There was Greek mythology, Romans named it after the god of war,
War, of
Mars,
course.
and then named March the month of March, because that's when
Yeah.
you would go to war every year. That was war
I mean,
month.
it's really
was
hard
get
to
out
wage
there
war in the winter. I don't know if you've tried it, but it's a bad
Yeah.
plan. Don't do it.
Okay, it's not cold anymore. We can get
Yeah.
out there and where do we? Well, what's the orange dot say?
Yeah.
That's who we go to war with, and so I think that the average person would go, well, that's silly. Like of course, none of us believe in this god of war Mars anymore. We now know it's a planet, but as soon as we knew it was a planet, we projected our own mythology on it again. As soon as people looked at it with telescopes, someone thought he was seeing rivers. An Italian guy described them as channels. Said canali or something like that is the Italian word. It got mistranslated as canals.
Yep.
And I was like, you know what? I bet canals were, this is late 1800s. I was like, I bet canals were like really popping off. They were like really exciting back then. And so I went to see, and it turns out that I was able to quickly find evidence to confirm the narrative I was seeking. That Suez Canal had just finished like 5 years before this. They were planning the Panama Canal. Engineers were like the rock stars of the time. This is all exciting. This is the pinnacle of human innovation.
Yeah.
And
so of course, it's at the forefront of someone's mind to think about, well, these should be canals.
So then someone looks through a telescope and pareidoliizes, if that's the way to say that, I doubt it, but sees too many patterns. It projects their own beliefs on this with this new technology, granted low res, and sees, and they're like, oh, there's not just some of these canals, there's a zillion of these, and this is where the idea of Martians first came from, and then there's War of the World that it gets broadcast over radios with these satellites and all this, and then people are like, oh my gosh, what happens if these Martians come and attack, and then I think they're gone now. They it looks like they may have died. Oh, could that happen to us? Did they overdo it with the canals? Maybe they made too many canals. Are we making too many canals? It was all the it was the way in which the human mind, and so now we have rovers and powerful telescopes, and now we're like, maybe we can turn the whole thing into a dome in 10 years, and we can move an entire civilization, and it's slightly more grounded in reality. A civilization 10,000 times more advanced than ours might do well to hedge bets on other planets or something like that in case an asteroid comes around. Sure, I'll give you that. But it's a leap to say that we're going to move billions of people in 20 years or so.
That does seem like a leap.
But it's, rockets are the big, this is
I was at a fantastic DARPA meeting talking about bio-inspired terraforming. Yeah, no, it was a great meeting, but
so like I guess what I'm saying is like we're always going to be advancing technology and understanding and gaining knowledge and having more, ideally, potentially, seemingly, hopefully having better and accurate more models of, and then you take that information and project it onto minds, and we make these, we turn everything into grand cartoons and wild, very scary or very dreamlike, opportunistic ideas. And I think that the only way to solve that is to get through to people that, like, this is the concept. This is the part of the human condition. Yeah. When ambiguous stimuli comes in, this is how we can expect ourselves to maybe react to it. So how do you factor it in? So how do you take the newest cutting edge information about, like, say, mathematically modeling crowd behavior, disease and pandemic, something, and then translate that to people without it turning into gods of war and all of
goodness. Well, so I think it's as much art as science, right? It's math. So there are decisions being made and then rules, but really it's about increasing our understanding. How do we stop it from being gods of war and the mythologizing of non-scientists and how to play with it? Hopefully we explain it really well.
Right.
And we explain what we're doing. And we say, you don't have to understand it, but you should see the process of what we're doing. And these are the things we've been able to explain or do or help or create that you've benefited from by this process before, that you do trust, that you take for granted, that has made your life better without you thinking, where did this come from? And that was science also. And the path wasn't smooth. We'd have a tendency to also assume that it was better in the past, that we didn't make any mistakes, that we knew instantly that this thing was good and we did it, and we've always known it was good and we do that. And the answer was, no, there's a lot of things that went wrong, but we figured out that we did something better. And then we stopped doing those wrong things. And now we only really remember, like, we do the right things in those cases. And sometimes also in parallel, we discover, like, whoops, that thing we thought was right isn't. And we'll stop doing the wrong things and we'll do the better things. And then we'll do that until we discover a better thing.
Man, it is.
Modernity
is so frustrating because it's the frustrating aspect of communicating things isn't that like people can't get something. It's like it's about like you tend to get frustrated with the people that you care most about sometimes. Like, oh, why can't they know better? Boy, if my best friend would just see things a little closer to the way that I would see them, And I don't know. It's like there's a weird with the world built on so many incredible counterintuitive things that technology has provided for us. There's like this intuitive, like almost uncanny valley. Yeah. Well. Like feeling.
Okay, so this is more speculative than I usually get in our conversations.
That's what I was hoping. That's what the people like. The people love speculation.
So I'm gonna spend a minute being religious of all things.
Okay.
So I'm in many ways I am not a religious person, and in this particular way I really, really am.
Okay.
So I grew up Jewish. I still identify as Jewish in a very real way. And in the portion of Judaism I grew up in, there is no greater way to love God than to study what God made. And to go and have the humility to go, I can't understand God, but I can get closer to understanding the mind of God by studying and understanding the creation of what's around me, and to find God in each piece.
Right.
And so while I don't necessarily subscribe to the deity part of that, I do subscribe to the holiness of realizing that our understanding of everything will always be imperfect, and it is still glorious to improve the understanding towards better.
Right.
And I think science does that. Science goes, we won't get this. And so that frustration that you talk about, I think also is that opportunity to dedicate yourself to the ever-increasing, shared, combined, not personal, but collective understanding.
And I'm saying, like, it's I get frustrated with myself and everything. Yeah. It's just I'm not even talking about my own frustration. It's just the palpable amount of frustration that there is within society.
So I mean, that's the thing that I think I personally wish we shared more, because I do think that the world is wondrous, and that a way to deal with that frustration, because I am also frustrated with a bunch of things.
Yeah.
But a lot of the way to deal with that frustration is to share the wonder of being able to improve.
Right.
And we don't need to agree on what improve means, as long as we agree that we're working towards improving and we're doing it together.
I think that's a wonderful message. Of course, I could talk to you forever, as usual. But we should wrap up. Is there anything that you want to direct anyone to, or tell anyone, or any closing?
So I think that the biggest closing thing actually is I love how much we always discuss when we talk to each other. And I think it's valuable for me to say, the notion of our center, of the APPEX Center, is to be this broad. And part of what we're doing also is not restricting the questions we ask to scientists. So if any of your non-scientist listeners listen to this and go, I have a thought, how about this question having to do with why in some cases diseases might be safe from expanding into outbreaks and pandemics, and in other cases they may not be. A possibility might be that scientists go, oh, we know that one, the answer is this. But another possibility might be that scientists go, oh, how would we think about that? And we have twice a year, we have a mechanism for everyone in the world to be able to put on a website, here's an idea about this, what does everyone think? And collectively try and construct a careful scientific question together. So if your readers are interested in this kind of broad-ranging, let's talk about philosophy and math and science, behavior and frustration and trust, and how do we know this, and what would we do about that? And when do we decide to act, and when is it okay to just go like, I don't know, someone told me. Those are all ways that hopefully our center engages with non-scientists to make sure that we're, as scientists, asking questions in ways that aren't just limited by the way science asks things.
Right. I would say from someone without any college background that got interested in learning more about science and science communication, generally it has always been the case, but I would love to, speaking of myths that I would love to dispel, is one that like science is some like sneaky, closed off, classified thing. I think it's because there's, the idea of like authority, like governments, military or something that there are like things that happen behind closed doors. Of course, militaries have like secrets and confidential things and whatnot. And I think that it's a byproduct of people's respect of science in some ways, that they lump them in with this like authority where they're like, oh, there must be some like classified thing going on that I don't have access to. And if there's one thing that I wish I could get through to people, it's like there's the science sections right there in every bookstore. There's open science opportunities all over the place.
But there is one thing that I do want to think is a pitfall that I do want to avoid in this conversation for your listeners. I know this isn't what you mean, but I do think that that science does have a little bit of policing about when science is done well. And so lay people who haven't been trained in science can occasionally propose things to scientists and have the scientists go, no, that's not done well. And scientists don't always provide detailed feedback about why.
Right.
And that can feel like just a cabal restricted society. And it's not meant to. It's meant to be like, no, there's a process by which we've tried these things in other ways and it's not reproducible, or it's not, we messed it up that way. Don't do it that way. But we don't always stop and say like, oh, here's the 50 years of history that tells us to do it this way and not the way you just thought of.
Yeah.
And that can feel like an authoritarian, restrictive society.
Right.
And really all it is just learn more about why we said no.
Right.
Or ask us, like, why was that not good?
Right.
Because we never have no reason. We always have a reason. And if the reason is bad, come back and push back and be like, are you sure? And we'll be like, here's the 7 published studies. Or instead we'll be like, oh, no, maybe I'm not sure.
Yeah.
Crap. So.
Yeah, well, I have a zillion things I'd love to talk with you about there as well, but it's been way too long.
Thank you so much.
Let's do it again soon, and thank you so much, Nina.
Thank you.
All right, everybody. Hope you enjoyed that. If you have questions, you can always write me. Go to shanemauss.com, but you can also go to the contact page, but you can also go to the contact page at APPEX.org, and you can find resources there, and you can reach out to the good folks at APPEX and ask them questions of your own and get more engaged yourself. I think it's a really cool opportunity to all of us kind of learn together and have the opportunity to access information together and think all this through together, and we all, every single person on earth should be wanting to make the best use of the best information available to them, and even if our particular tribes don't always do that, we can always be a source of influence in whatever tribes we happen to find ourselves in. Of course, we're all going to have a little bit of in-group and out-group stuff from time to time, and we're always going to have uncomfortable conversations and a difficult time agreeing with one another. And I really do believe, like this discussion today, that things like math are a way that we can go like, all right, we can at least agree on this first and start small and work our way up in complexity together. So I hope I'm not being naive, and even if I am, I don't care. It's a dream worth dreaming. So you guys are great. Thanks for listening. Thanks for watching. I'm gonna go paddleboard.